This is the 9th in a series of videos in which I've been putting together a power supply built around a Ryden RD6006 switching controller. In previous videos I built a switch mode version of this, and this particular version has a linear back-end power supply. Now of course the Ryden is still a switching supply. The difference here is that the back-end supply in this unit is linear and not a switch mode supply as was in the first one that I built. In this video I'll be comparing this linear version against the switching version that I built. So I'm comparing one Ryden with a linear back end against a Ryden with a switching back end. I'm not trying to say that Rydens are good or bad, and I have no affiliation with Ryden whatsoever. I'm not trying to market or promote these supplies. I'm simply demonstrating something that I've put together here. And the main purpose of these videos is to show that you can build things yourself. You don't need to buy off the shelf transformers, or you don't need to use things the way they're intended to be used. It's a case of experimentation, and you can put together something that is perfectly usable for a very low cost. So I had these transformers lying around. I could have bought an off-the-shelf transformer. However, if you've seen the voltage drop on these two transformers, these give us around 450 VA. If you'd gone for 400 VA transformer, you'd get far more voltage droop, you'd have a bigger problem. But it kind of depends on what you're aiming for. If you wanted to achieve and guarantee the full 60 volt output, you could of course use thicker wire on the transformers. You'd get less voltage droop, and therefore the output would stay higher at higher output voltages from the Ryden. But I wanted 55 volts peak output from this. I'm probably actually going to get 60 volts anyway, but it was designed around achieving a minimum of 55 volts. How you go about it is entirely up to you, and that is the point of my videos. Don't be afraid to experiment. It's always interesting. You can always tear it apart if it doesn't work and try something else. But this is the joy of electronics. It can be very rewarding, can be very frustrating, but the main thing is give it a go. So that said, what we're going to look at in this video is comparing this unit directly with the switching version. It's not going to be an in-depth technical review. We're not going to look in detail at the EMC for these units. There are very specific setups for that if you're interested in looking into that. The difference between these two is probably going to surprise you. So the difference between this one and the switching one is almost certainly going to surprise some people. But we'll start with this particular unit. Now, as I said, this is not the only way to go about building this. It's not even necessarily a good way to go about doing this. But we'll look at the results and see what we get. But as I said, it may be quite interesting for some people to see just what the difference is in the two approaches to building one of these. There are some downsides, but in my opinion the upsides far outweigh the downsides. So as ever, sorry for the flickering on the Kunkin electronic load. I can't do anything about that. Hopefully it won't irritate you too much. So what I've got here is the supply's been running now for about 2 hours. It's running at around 330 watts, so it's set to give 58 volts out. It's been running into the load, and what we'll do to start with is look at the inside through the thermal camera and see what's getting hot. If you do this with a switch mode version, you will see that the switch mode supply at this point will be extremely hot. It will be up around 60 or 70 centigrade, and certain parts will be even hotter. What you'll notice here is that the temperature down here, and that's the hottest temperature in the system, that's the temperature of the rectifier heatsink, is around 44 centigrade, and it's stabilized at 44 centigrade. It's not rising anymore. But if we look through the thermal camera, we can see that everything is fairly cool. The only things that are getting warm at all are actually the thick cables. These are the thick copper wires between the transformers. So that's these wires here. These are 2.2 millimeter wire. So you can imagine that they're not actually as hot as they look on the camera. They actually feel cold, but they are the hottest part of the system other than the rectifier. They look hot on the thermal camera because the thermal camera gives a gradient of temperatures within a system, within a given view. but if you look at the transformers themselves, you'll see that they are actually still cold. They're not getting warm at all really. The capacitor bank is showing as black, so that is fine. We're not reaching any issues with the capacitors. The hottest part, of course, is the rectifier heatsink, and that will be up around 44 degrees as we see on the display. If we look over to the side, you'll see the hot thing in the background is just the equipment that's sitting behind the electronic load. The load, of course, is blasting out a lot of very hot air. That's how it keeps itself cool, but the load itself is actually quite hot. And then off to the right we've got the variac, and that's cold. So as we can see, the transformer's been on a couple of hours. It's been running very near peak load for a few hours, and we are barely seeing any temperature rise other than in a couple of the conductors. But as I said, they're nowhere near to getting hot as such. They're still well under 30 degrees centigrade. So it's looking very promising. One thing here that is an advantage we'll come back to in a few minutes is if you look at the output from the variac. I will come back to this later. Hopefully you can read these. I've tried angling the variac to make the displays a bit clearer, but I'm still not quite sure if they're visible on the camera. I can't quite tell looking through the viewfinder. But what we're seeing at the moment is 1.79 amps at 247 volts. This is turned right up to the current mains voltage, and we'll come back to these readings later on because they are quite interesting, and it's something that will become more interesting when we compare it with the switching version. Now, before we go any further, I've said in a few videos previously that you shouldn't run equipment necessarily without the covers on, because certain parts of it may be thermally managed and require that the cover be fitted. So before I go any further, just by way of a very quick demonstration, it doesn't really relate to this video, but it's something you might find interesting. This has been running with the top off. With the top on, the internals should actually be cooler than they are. So although the fan has kicked in because we're above the 40 centigrade limit, it's not really doing much, it's just sucking air in from the sides. But as you can see, the temperature is up at 44 degrees. What I'm going to do now is put the top cover on. Let's be careful here because obviously it's switched on. Okay, so top cover is just resting over. It's not screwed on, of course. Now, a lot of people might expect the internals to start getting hotter with the cover on, but what you'll notice is that the internal temperature will actually start to drop, and that's because the air is now going in through the front of the case. It's been drawn down through the enclosure and blown out through the back, and that will make a fairly big difference. We've already gone down to 43 centigrade. It was 44, and it's been sitting at 44 for over an hour. And I've just covered it up, so you might expect it to go higher, but this will now continue to drop. The temperature will probably end up down around 38-39 degrees centigrade under these conditions. So that's something to bear in mind if you're designing something and you're checking the thermal performance and you want to attach probes and sensors to monitor temperatures. Make sure you do it with all the covers in place. It doesn't follow necessarily that removing the covers will make it run cooler. Removing the covers can make certain parts run hotter, so that's just something to bear in mind. The reverse is true, of course. You could end up with a hotter enclosure if it's not properly thermally managed. Okay, so I'll leave this running for a few minutes and we'll see if the temperature drops any further, and then once we've done that, I'll start comparing the two supplies. Okay, so it's had about 5 minutes. The temperature has now continued to drop. We're down to 37 degrees. Out of interest, what I will do now is take the cover back off and we'll look at it back through the thermal camera, and we'll see how it looks through the thermal camera once the cover's been on for a few minutes. It's still running, of course, so we'll be heating up again. So if we look at it through the thermal camera, now it does appear that things have heated up, but in reality what's happened is certain parts of it have cooled down. So if you look at the cables along this side that were glowing red on the image before, you can see they've now cooled down because they're in the airstream, and it makes it look like other things have heated up because the temperature spread across the entire enclosure has dropped. But if you look at the actual temperatures being displayed, you can see they've actually gone down. So we're down now probably 2 degrees over what we were seeing before. Some of the hot spots have gone, but as you can see, nothing's getting drastically hot. We'll see that the if we keep watching for a while, we'll see that the heatsink temperature will start to rise again because we've taken the cover off. But the point is that the thermal management in this is fine. We're not going to encounter any problems. With the cover on, it runs cooler than with the cover off, and with the cover off, it doesn't really get very warm at all. So in other words, this will be absolutely fine to run at maximum output indefinitely. Nothing's going to get unnecessarily hot. And that's what you want. And again, we've got the capacitors directly in the incoming cool air stream, so these will run very cool, have a nice long life. The hottest part is right by the extractor fan. So it's looking good. What I'll do now is I'll get the cover screwed in place, and then I can start doing a comparison between the two types of power supply. I thought you may be interested in having a quick look inside the case before I bolt the cover on. I've shown this briefly in previous videos, but haven't really explained in detail what I've done here. Now, this is not the only way you could go about doing this. It's not even necessarily a good way of going about doing this, but it's what I built, and this is what we're testing, so I thought I might as well explain what's in here. But the point is, feel free to experiment. You can build these however you want, and that's kind of the point. It's, have fun, try things out, see how they work, tear it apart, try something different. And the more you do that, the more you can learn doing it, the more interesting it becomes, and ultimately you end up with a usable piece of equipment. So what we've got here are the two transformers. I showed these being wound in previous videos. This arrangement is a bit unusual. It's two 120 volt transformers, and I'm in the UK, so the mains here is a nominal 240 volts. And the way these are configured is the two 120 volt primaries are wired in series, and the two 24 volt secondaries are wired in series, and then that will give us an output once it's smoothed, rectified, of around 70 volts, just under, and that's the voltage that we feed into the ride-on controller. You could wind these with thicker wire if you wanted to reduce the amount of droop, but we're at the point with these two cores where really the majority of the droop is caused by the core. In other words, we're reaching the ability of the core to transfer power, and so if we put much thicker wire on, it would make a bit of difference, but not that much, maybe a volt and a half. Okay, so what we're looking at here, of course, are the two transformers. I made up some custom mounting posts, machined from Delrin rod, and that means that this metal bolt and the washer on top is not electrically connected to the bottom. So in other words, if we short this to chassis, it's not going to result in a shorted turn through the transformer, so it makes it much safer. Whether you do that or not is up to you. It's just, if you don't do that, just bear in mind that you mustn't short the top to chassis. We've then got the rectifier heatsink. This is bolted directly to the bottom of the chassis, and that means that not only do we have the benefit of the heatsink cooling the rectifier, but also the heat is bled down into the chassis and it dissipates that way as well. This thing runs quite cold. It's, as you saw, it gets up to around 40 degrees with the cover off, but because with the cover on, air is being drawn down through here and past both sides of the heatsink, this temperature drops a lot once the cover's on, and it sits at full load. It sits at about 35-36 centigrade, and that's obviously very reasonable. These rectifiers are rated up to over 100 degrees C. We've then got a small board here that comes with the enclosure kit, and this is to control the fan on the rear of the case. The sensor from this is passed into a hole I drilled in the heatsink, so it's in very good contact with the heatsink. And the way this works is it takes power from the capacitor bank, steps it down, and then it uses that to monitor the heatsink temperature. If that temperature goes over 40 centigrade, it turns on the fan. There is some hysteresis, it turns off again, I think, at 38 degrees. but it means that the fan doesn't always run. In fact, it hardly ever comes on. It only comes on if you run it at full power for more than probably 15-20 minutes. The rectifier is bolted to the back of the heatsink, and all the wiring from it is doubled up. So this is silicon insulated wire, and I've doubled up each of the conductors, not necessarily just for the peak current handling capacity, because we're only looking at a peak current of about 8 to 10 amps. This is just to keep the voltage drop and heat generation to a minimum. If I turn the unit round, what we've got on this side is of course the mains power input socket, the main switch, the two primaries wired in series, and these are on the opposite side to the low voltage wiring, and then we've got the capacitor bank, and this is something I bought off eBay. It's meant to be used as a plus minus supply bank, but I fitted the capacitors on one side in reverse, so if you were to take this out you'd see that half the capacitors seem to be fitted backwards, and what I've then done is, you can see there's a thick link here, and that's linking the what would be minus output to the positive output, but don't worry, it's not shorting anything out. It just means that the two halves are in parallel and it's not going to blow up or catch fire, and that just means that I can treat this as one large bank rather than two smaller ones. The power from the rectifier comes into the screw terminal on the left here, and then the two wires feeding the rider controller, that's these two wires here, come out of the other spare screw terminals. The AC side of it is not used at all. And then at the front we just have the rider controller. We've got the power going into it from the capacitor bank, and then we have the output, which is this cable. I don't know if you can see it or not, there's a cable here, and that goes through to the temperature sensor that's also on the rectifier heatsink, and that's the sensor that we derive the reading on the display from. So that's all that's in there. It's very simple. The total time for me to rewind the transformers and build all this is less than 12 hours, so although it looks like a time consuming thing to do, it's not that difficult, it's not that time consuming. It might take you a bit longer the first few times you do it, but it's well worth it. If you're looking at experimenting with transformers, if you are doing a particular test or experiment, you want to try something, you could well spend 4 or 5 hours on the internet trying to find a suitable transformer. You then got to wait for it to turn up, whereas you could wind one in a few hours, and it wouldn't really cost you much more than a few pounds for a few reels of copper wire. And it does save an awful lot of time. As I say, it might seem like a long-winded thing to do, but it's easy. It doesn't take long, and it will give you very quick results, and more importantly it gives you the satisfaction of knowing that what you built is entirely your own design. Okay, so I'll finally get this cover on, and then we'll start comparing the two supplies. So here are my two supplies. Obviously they look identical from the outside. Turn them round, and on the back again you can see that they are identical. If you do build one of these, I suggest putting a sticker on the back to say what the voltage is. It doesn't matter so much with the switching version, but of course it does matter with the linear version, especially if you're building a 120 volt only version. Okay, so as you can see from the outside there's nothing to distinguish them, so I'll start doing some actual comparison. The first thing is the disadvantage, and it is one of the few disadvantages. You probably can see where I'm going to be going with this. So I've got a scale, it's reading in kilograms. If I put the first unit on, I don't know if this display is going to come out clearly on the camera, but we are seeing 2.22 kilograms. And I'll let you try and guess which of the two supplies is which. So I'll now put this one on. And we're seeing 7.2 kilograms. So of course this is the linear one. It's over 3 times the weight of the switching version, and that's one of the few disadvantages with the linear supplies. They do tend to be heavy, and of course 360 watt supply is quite a beefy supply, so it's always going to be heavy, but the Rigel supply I have, the DP832, handles less power and is actually heavier, so it's not an unreasonable power. So it's not an unreasonable weight for this power of supply. Okay, so as I said, this is not going to be an in-depth test on the absolute EMC performance of these, or the absolute power, or the absolute accuracy. What we're looking at here is general practical use of these supplies and how they compare to each other in an average lab environment. So I use supplies like this for a wide range of things, from repair to development, testing, and sometimes in the lab I need specific performance from the supply. If I need very high performance, very low noise, I wouldn't use one of these, and there's very few supplies I would use, but that's not what they're for. But what I want to demonstrate today in this video is the relative general performance of the two as it relates to how you might want to use it in your lab environment. So the first thing is something you might not always consider, is that if we have two supplies like this, we might have scopes and analyzers and all sorts of equipment plugged into the main supply in our lab, and a lot of time you will encounter problems that aren't always coming from an obvious source, and it can be confusing sometimes as to where that noise is coming from. So I've got two mains cables. The one labelled L is for the linear supply, and the one labelled S is for the switching supply. So at the moment I have the linear supply plugged in. I'm going to bring the Kunkin electronic load in, so I'm just going to move the camera across so you can see that as well. I will now plug the load into the linear supply, which is the bottom one. So throughout these tests I'll keep the linear supply on the bottom. Incidentally, one thing that is nice with the linear supply, it's a minor thing but it's something that I quite like them for, is this. If you try and plug this into your switching supply, it will move around because it's obviously light, whereas if you do the same thing with the linear supply, it's not going anywhere. It's a minor trivial thing, but it's something that I do like. Okay, so I'm going to leave this voltage set the same for both of these tests. I'm going to power up the Variac, and what I'll do now is switch the supply on. We've got the electronic load set to 10 ohms constant resistance, and we're now getting about 332 watts out of the supply. So it's set to 58 volts. We're getting 332 watts, and as you can see it's working fine. However, if we look at the Variac, I'm hoping you can see the readings on this. I'm just looking through the viewfinder on the camera. I can't really see the left hand display very clearly. Hopefully you can read it. If not, it's saying 1.78 amps, and this is where you need to be fairly cautious when you're looking for issues that you're having with supplies. Power supplies can be very misunderstood, and they can be the source of a lot of issues, not always obvious ones. So if we now look at the power, there are two types of power you need to consider with AC. There's real power and apparent power. So here we're looking at a DC output target of 360 watts, and we're talking about transformers that have a VA rating. The VA rating is nothing more than current multiplied by voltage, and it's not necessarily the same thing as real power, because the real power is the power we're actually getting out of the system. Whereas if you just simply multiply the voltage and the current to get the power, because the voltage and current are not necessarily in phase, then the real power is not necessarily, and very rarely is, the same thing as the apparent power, and the difference between the two is normally referred to as a power factor. So if we try to calculate the power that this gives us, so if I multiply 1.78, got my trusty calculator here, by 249, then the value we get is 443. So if you make a note of that, 443 watts, that's not too bad. We're getting 334 out. So for the overall system, we're getting a loss of about 110 watts. But bear in mind, that's the difference between the apparent power and the real power output. Okay, what I'll do now is swap the supplies over. So I'll connect the switching version. So everything else is staying the same, I'm not changing any settings. I'll now turn the variac back on. I'll set the supply up to give us the same, so that was 58 volts. I'll turn this on, and we can see we're getting exactly the same power that we were before. However, if we look at the current on the variac, we'll see it's higher and it's climbing, and it will continue to climb as the switch mode supply heats up. So we're now over 2 amps and it's still climbing. So you could say, well, that's because we're getting a higher voltage going into the Raiden, but bear in mind the Raiden is a switching controller, so that's not going to make that much difference. It would make a difference if it was linear, but it's not. It's a switching controller. So we're now up to well over 2 amps. This will continue to rise up to quite a high level, but if we take the current value, remember before we were getting an apparent power of 443 watts. If I now work this out, so 248 times 2.07 is giving us 513 watts. So that's a huge difference. It's getting on for 100 watts more apparent power, and that's because the power factor that this switching supply is creating is far worse than the linear version. In other words, the current and voltage are way out of sync on the switching supply, whereas in the linear supply it gives much more predictable results, and that in turn means that the linear supply is going to be effectively injecting far less noise back into the mains. You can see this is still continuing to rise, and this gets very bad. If we go up slightly in terms of mains voltage, you'll see that this will tend to track way out of proportion to the amount of power that we should be seeing it change by. So in other words, it's very important to bear in mind that a lot of the noise you'll see from the switching supply is going back down the mains cable, not necessarily coming out of the front of it. It's also fairly unpredictable, and it will of course vary depending on the power supply that you use, the switching supply that you use. But just bear in mind that a lot of the problems can be coming directly from the fact that the power factor for your switch mode supply is going to be very poor, and they always tend to be poor. You can find expensive supplies where they're quite good, but the switch mode supply is taking huge current spikes, and so the power factor is always going to be fairly bad. Whereas the linear supply is taking a much more kind of averaged out power from the mains, and so that generates a far better power factor. So that's the first thing to bear in mind, is the power factor for your switching supply is going to be quite poor, and that is where you will see a lot of the noise coming from that we will be looking at later on. Okay, so the next thing we'll look at is the noise that we can detect coming out of the supply. Now what we'll be looking at here is not the real noise in isolation coming out of the supply. You'll need to spend a lot of time and effort getting a setup if you want to accurately measure that. But we'll be fairly close to looking at the noise coming from the Raiden switching controller, at least on the linear version of the supply. But more importantly, what we're looking at here is using these supplies in a lab environment. And I'll come back to what I mean by that in a few minutes. I'll just swap this all around so we can get the scope on screen, and then we'll start looking at the noise coming out of these two supplies. Okay, so the setup I've got here is both supplies are connected to the mains. They're connected through a filter block, so as much as possible we're not getting noise coming in to the supplies from the mains from other devices. And also it isolates them to a certain degree from each other as far as the mains cabling is concerned. When you're in a lab environment, In all honesty, the absolute noise you're seeing, it doesn't really matter whether it's coming from inductive coupling through to cables or down the mains or even out of the front of the supply. What matters is what you're picking up, because that's what you're going to pick up in your normal working environment. And if the differences are fairly subtle, then you'd be well within your rights to say, well, is that instrumentation, is it the way I've got the cabling laid out? It could be any manner of things. But what I want to demonstrate here is a fundamental difference between these two supplies. So what I've got is the supplies are configured exactly as they were for the previous test. They're set to give 58 volts out. Again, we've got the switching supply at the top, the linear supply at the bottom. They're going through to the Kunkin electronic load. I've got the current clamp I showed previously connected to the positive terminal of the output from the ride and supply, and that's feeding channel 2 on the scope. So channel 2 is effectively the current we're seeing coming down the cable in isolation from the EM voltage emissions, if you like, that may be interfering or causing noise within the cabling going to the scope. Channel 1 on the scope, which is the yellow trace, is the actual AC voltage coming out of the supply. So I've got a small capacitor here, so it's isolating the DC content from the supply because I'm not interested in that. And I've got the scope set to AC for both channels. So what we're looking at on the scope is just the AC content of whatever's coming out of the supply. And of course we've removed the DC from it. On the ground lead from the scope, I've got a ferrite, and that's there. If you looked in a previous video, you'll probably see why that's there. But it's intended to effectively eliminate as much as possible the interference we're getting that's not due to the supplies. So in other words, it kind of gives us what amounts to a very good ground at this point in the system, and that means that what we're seeing on the scope is more related to what's coming down the probe. Okay, so you can see on the scope that we're getting some noise already. The scope is set to 2 volts per division. I'll just switch the ride and supply off so you can see the difference, and you can see that noise disappears. I'll turn the scope sensitivity up. So I'm changing the sensitivity of channel 1. We're now up to 100 millivolts per division. Both supplies are turned off. What I'll do now is turn on the switching supply, and although the ride and output's turned off, we're picking up a lot of noise. So of course this is not coming out of the ride and power socket. So I'll turn the scope sensitivity down, but you can see this is what we saw in a previous video. This is inductive coupling coming through to the cabling, and although you could say, well, it's not coming out of the front of the ride, and that may be true, but what is also true is that if I was in a lab environment and I was seeing this, it would be a bit of a nuisance. It doesn't matter where it's coming from, what matters is the fact that it's there. So we'll go back up to 2 volts per division on the scope. What I'll do now is turn on the output from the Ryden, and you'll see we're getting a bit more noise. And now I'll turn on the electronic load. So we can now see that these noise spikes have grown quite considerably. We're up to about 6 volts peak to peak, and they are directly in phase with the current that we're picking up using the current clamp, which uses a different method of measurement and is more isolated, if you like, from the inductive coupling that we're seeing. So in other words, the spikes we're seeing are real now. These are what are coming out of the ride and supply. If I disconnect the cable, you'll see that they go away. I'll reconnect it, turn the load back on, and you can see they're consistent, they're there all the time, and we're getting, as I say, about 4.5, 5 volts peak to peak noise, and that is obviously quite poor. So, you know, the instant thing to do is point a finger at the rider and say, well, it's a very bad switching supply, and it can't really be used. What we'll do now is we'll swap the probes over to the linear version of this supply. So I'll just turn that off. I'll swap these over. Okay, so I've swapped the cables over to the linear supply. I'll turn this one off, I'll turn it off at the mains as well, and now I'll turn on the linear version. So wait for it to finish booting up, which it has. So exactly the same arrangement, and already you can see there's a huge difference on the scope. There's nothing really apparent on the scope trace at all. I'll now turn on the output of the Raiden. Again, still nothing on the scope. I'll turn on the electronic load. Okay, so what we're seeing here is just the mains hum. That's not coming out of the Raiden, that's just what the cables are picking up. And you could easily remove that by just rerouting the cables, but that's not what we're looking at here. What we're looking at is the switching noise, and as you can see it's far less. In fact, there's nothing really visible on this setting on the scope at all. So we'll start zooming in. So we're at 1 volt, 500 millivolts, 200, and to eliminate the AC that's causing a problem, I'll do a single capture. And what we can see is this is now 100 millivolts per division. So we're getting about 300 millivolts peak to peak, and this is the switching noise that we are seeing coming from the Raiden supply. So this is the actual switching noise that we have been talking about, and this is the impulse that we're seeing coming out of the Raiden, and this is the actual noise that we need to measure. So you can see here it's 350 millivolts per division. And don't forget, this is very close to full power, so this is probably as bad as it's going to get, and in my opinion it's quite reasonable. It's not going to be as good as a true linear supply, but you wouldn't use this for very sensitive testing. But as you can see, it is very reasonable. There's nothing really here that's going to prevent you using this supply. Now again, I stress I'm not affiliated with the manufacturers. I'm not trying to promote or sell these. I'm just presenting what I found with the two versions of the supply that I've built. And what I'm trying to get across is, experiment with design. You're not tied to doing things in one way. So what I'll do now is swap the cables back and see if we end up with the situation we had before. So I'll turn the load off, I'll turn the Raiden off, and I'll turn the Raiden off at the mains. Swap the cables over. Okay, I'll turn the switching supply back on, and already we're off scale on the scope, but I'll leave it set where it is, and we'll turn the output on, and now we'll turn the load on. And if you now look on the scope, so although you could argue as to where the source of this noise is and whether it's coming through the mains, through inductive coupling, or actually out of the supply itself, firstly, it's not being produced solely by the Raiden. As we've seen, exactly the same sort of controller in a linear version will give you very much better results, and it doesn't matter where it's coming from in a lab environment. If you're trying to make sensitive measurements on a piece of equipment that you're powering from this, then all bets are off. You're not going to be able to do anything sensible. I'll single shot capture this so we can have a closer look at what's coming out of the unit. And we can see again we're getting several volts of noise. I'll turn channel 2 off, we're no longer interested in that one. So we're looking at probably 6 volts peak to peak, and that is obviously terrible, and it would be easy to blame the Raiden. But again, I'll keep the scope on this scale, and one last time we'll switch back to the linear supply. Okay, I'll turn the supply back on. So bear in mind we're on the same scale on the scope. The settings on the power supply are the same, and as you can see, this linear supply is far more usable than the switching one. I've done a single shot capture and we can see that on this scale, compared to the switching supply, and when I say switching supply I mean the switching back end supply, and there is no comparison whatsoever. This is now the linear version, and we can see if we zoom in there is very little noise. This is just scope noise, and I'll do a single shot capture at 500 millivolts per division. So now we're starting to see the noise that's coming from the Raiden itself. We'll do another one now at 200 millivolts per division. So again, we're looking at maybe 300 millivolts peak, which is extremely good. So I'll do the same thing now, but at around 100 watts or so. So 90 watts. Get the scope running, and again we can see the switching impulse voltage is about the same. It's about 300 millivolts peak, and with the same setting on the switching version we'll see if we get the same results. So I'll set 30 volts on this unit, we'll power it on, and we can see straight away that the results are far worse. In fact, you're getting on for an order of magnitude in terms of the difference in performance between these two power supplies, and the only difference is the back end power supply. The top one's switching, the bottom one's the linear one that we built, and I'm hoping that this clearly demonstrates that building the linear version is more than worth the effort. With the results that we're seeing here, yes, the switching version will work. It'll give you a quick and easy solution. You'll get a power supply that will be good for charging batteries, that sort of thing, but it's not something I would consider using for a lab, whereas the linear version I think is quite reasonable to use in a lab environment. I won't go through step responses, that sort of thing. The linear one is actually a lot better in terms of step response because it's got a big capacitor bank, whereas the switching version has to convert any missing energy on the fly, so to speak, whereas the linear version has the big capacitor bank feeding into the Raiden, so it tends to be much better in terms of step response. But to be honest, both are quite reasonable in that respect. It's mainly in terms of the output noise that we see an issue with the switching machine, but we shouldn't just point a finger at the Raiden switching controller. As I've again hopefully demonstrated here, it's not down to the Raiden controller. This noise, although it's manifest out of the supply, it's actually created mostly by the switching back end supply itself. As I say, I'm not affiliated with Raiden. I don't know who manufactures these. I don't really care who manufactures them. I bought these and I'm just demonstrating here a route you can take to build a good supply, and also the fact that I want to encourage people to experiment and not assume you have to buy something off the shelf. Okay, that's it for this video. Hopefully you found that interesting. I just want to stress here that I'm not trying to compare the Raiden controller against any other sort of switching controller. I'm simply comparing one Raiden against another, where one has been built with a linear supply and one's been built with a switching supply. I'm not trying to say or imply that Raiden's better or worse than other supplies of switching supply. I'm not trying to imply that the linear version is a full linear supply. It's obviously still got the switching front end, but what I'm trying to do here is demonstrate the difference between the two approaches, and I hope that I have made it fairly apparent that there is a difference and that the extra time and effort required for the linear version is well worthwhile. If you want me to do any more in-depth testing with these two units, then leave a comment. Otherwise, I hope you enjoyed the video.